VSEPR is an acronym which stands for Valence Shell Electron Pair Repulsion Model. It allows us to accurately predict the three-dimensional orientation or structure of covalently bonded molecules. The theory is rooted in the fact that around a central atom, let's take carbon for example, if we only consider its outermost or its valence electrons, we're going to be looking at 4 electrons. Now, the valence theory states that because electrons are negatively charged, they naturally repel one another. So what valence theory says is that we want to actually maximize the distance or angle between these negatively charged electrons. If we create structures in which the electrons on the outermost energy levels are as far apart as possible, then what we find is that the theory of pushing these electron pairs apart, as far apart as possible as we can into three-dimensional space matches experimental results. Let's take an example of carbon dioxide. Carbon dioxide is composed of a carbon and it is double bonded to oxygen. Carbon dioxide is a linear molecule because the farthest apart we can get these negatively charged electrons surrounding the central carbon is 180 degrees on either side. You could envision a carbon that has oxygens that are separated by less than 180 degrees. However, when this angle is not maximized, what you are getting are the electron clouds and the bonded electrons repelling. Notice that in the structure above, if bonds are made of electrons and if electrons are negatively charged, what we see is a 180-degree angle between the negative charge on either side of the carbon. In any other orientation, for example in the one shown here, one could envision this to be perhaps about 120 degrees, maybe a little less. In this case, the electron repulsions between these bonded electrons will not be minimized. So VSEPR theory states what we do is we orient molecules and bonds around a central atom such that they spread as far apart as possible, minimizing the electron pair repulsions between the bonded electrons. Now this takes on different notions of molecular geometry when one expands into three-dimensional space. In the examples shown here, carbon is double bonded to carbon on the other end. If it's a linear shape, in essence it's a two-dimensional molecule. Things get a lot more complex when you start thinking about 4 and 5 and 6 bonded pairs.